So in this video we're going to discuss point masses and how we can balance a system. And we're going to start with a very basic example, work up to a little bit more interesting example, and then we'll see from there how this will generalize. So say we have two items on a teeter-totter, for instance. One of mass m and one of mass 2m, and we need to balance this system. So we know that the lever, the fulcrum, is going to have to sit probably closer to the side where we have more mass. What we want to do is figure out how much more it has to be. Well, what we're going to do is we're going to look at the moments. The moments are the tendency of an axis to turn in one direction or the other. So the way we're going to get the moments is we are going to look at not only what the mass of an object is, but how far it is from the center. So for instance, maybe we call this distance x, and then we call this distance L minus x. Now, what we have is a system that we want to keep in balance, and what we'd like is for the 2mx, so that's that tendency to turn this direction, to be equal to L minus x times m. If these are equal, then our system is in balance. So let's see where it says we should put our fulcrum in order to have this thing in balance. 2mx equals ml minus mx. Add mx to both sides, and we get 3mx equals ml. I can divide both sides by 3m. The m's cancel, and I get it should be L over 3, or we can think of that as 1/3 L. So it should be 1/3 the distance in order to keep that system in balance. Alright, that's great for 2 point masses, but what if we have more than 2? I want to do a case where we have 3, and you'll see from there how it generalizes. So here I have 3 point masses, all with different weights. We don't know that they're the same this time. Last time we were doing m and 2m, so these could be anything, 10 kilograms, 1,000 kilograms, 1,000,000 kilograms. And their location along an axis. So what we need to do is, instead of just having 2 where we can set the moments equal to each other, what we're going to do is we're going to sum up the moments, and we want them to be 0. Now, depending on what side of x bar you are, the distance could be positive or negative, and that's why it will be able to add up to be 0. So let's say, this is arbitrary, but let's just say right here we decide to say, okay, that's x bar. Well, what we're going to do is we're going to sum up the moments. So m1, well, we need its distance from the center. We can represent that with x1 minus x bar. We're going to do the same thing with m2. Its moment is m2 times x2 minus x bar. And finally, we have our third mass, x3 minus x bar. And we want this sum to be 0. We could keep on going with 100 masses. This is going to be all you need to see how this generalizes. Now, what's nice about this is the x location minus x bar, it's going to be negative if it's on the left side of x bar. It'll be positive on the right side of x bar. So some of these terms will be negative, some will be positive, so it can add up to 0. We want to solve this for x bar. X bar is that center of mass. So m1 x1 minus m1 x bar plus m2 x2 minus m2 x bar plus m3 x3 minus m3 x bar equals 0. All those terms with a negative on there I'm going to put on the right hand side. All the terms without x bar or a negative I'm going to leave on the left hand side. So I have m1 x1 plus m2 x2 plus m3 x3 equals, now over on this side, I have m1 x bar plus m2 x bar plus m3 x bar. So on this right hand side, I am going to factor out x bar, and I get m1 plus m2 plus m3. Over on the left hand side, there's nothing I can factor out. It's just going to be m1 x1 plus m2 x2 plus m3 x3. So we can solve for x bar. We're going to divide by m1 plus m2 plus m3. So m1 plus m2 plus m3. So the center of mass for x is the sum of the moments over the sum of the point masses, which is actually just the total mass of the system. That's going to be really useful when we go to the continuous case. But what you can see is if I added more masses, we can kind of see how this is going to go. So x bar, if we have n point masses, we get to do I equals 1 to n of x sub n, m sub n, all over I equals 1 to n, the total sum of all the point masses. So this is our discrete case. You can probably already see as we take the limit as n goes to infinity for our continuous case, these are going to turn into definite integrals. Again, the denominator is just the total mass, which we've already seen how to find. The numerator is the same integrand except with an x in it, and we're going to see that in a couple of examples. So this is where the formula comes from for point masses, and then the next step is to take the limit as n goes to infinity for our continuous case, which is going to be the formula you see for x bar using definite integrals.